And I just wanted to take a moment to go over this question we did in class that got a little bit confusing. So here's the question once again, and then I'm going to walk you over to the solution I've put on the board and talk you through it. So let's just remember, we're looking at two boxes side by side. Here's an illustration of the system with the hand pushing it, and because we're going to treat this as one system, that is to say we're not going to think of these objects as individual but as all together, then I would draw this as a free body diagram for the system, okay? Noting that the mass is the combined mass of 5 plus 10. We know that the object's been pushed forward and that there's going to be friction on these boxes, and because we're only dealing with motion in the x direction, we don't have to worry about the combining forces in the y direction. So let's start with Newton's second law. Newton's second law tells us the acceleration of the system is the sum of all the forces acting on it divided by the mass of the system. So I'm trying to be specific in my notation there so that we're clear. So we go down a step, and in this case now, we're substituting for F net the actual sum of all the forces, which we agreed over here only involve an applied force to the right and a frictional force to the left. So this is what we have here. Total force in the system divided by the mass of the system. And I'm going to substitute in what I know. The applied force still is here, and that frictional force we can determine by coefficient of friction times mass times gravity, because we know the formula for force of friction. And let's substitute in our numbers. 45 divided by the, take away the friction divided by the mass gives us this for the total amount of acceleration. Okay, so now that we've dealt with this as a system and we've figured out the acceleration of the system, we would actually have to round that out in our therefore statement, but I haven't done it here. So let's look at now individual components. The objective is to figure out what is the contact force between these two objects right here. They're internal forces to the system. So the only way to figure out what the force is here is to think about these two things separately, because those two forces would cancel each other out when we think of them all together. And so we need to think of them separately. So here I've drawn the free body diagram of the first object. And let's think if this is understood. So we know that the object is being pushed, so there's an applied force. This is the one that's 45 newtons. We know that this object has friction on it, so I've indicated it here. And we know that if I'm pushing on another box, then the other box is pushing back on me. And that's why I have this, and I'm going to indicate it here, the force of box B on box A, right? So this box is pushing the big box, and as a result, the big box is pushing backwards on the small box. We end up with this. The same thing for the second object. This is the 10 kilogram one. Now, this object has, where is it feeling a force? It's feeling a force because of the first box, right? Object A is pushing on it, and that's what we feel right here, FA on B. And it has its own friction, so we have force of friction on B. Okay, so given that we are looking at this in isolation, now we're going to use Newton's second law, but we're only going to focus on this object here. So what we've done is we're going to write Newton's second law again. Okay, the sum of all the forces is equal to mass times acceleration. But now when we go to write in the sum of all the forces, we're just going to write in the ones that we see here. So what we have is the sum of all the forces is Fa on B to the right, take away the force of friction on B, has got to be equal to the mass of B. And I've swapped out acceleration of B with acceleration of the system because as a physicist I've realized that this object accelerating will be the same as the value we calculated altogether. Okay, so let's substitute in our numbers, and we figure out that the force, and we just had to rearrange, okay, bring this force of friction to the other side, which is what gives us here. And we get a force of A on B of 30 newtons. Now, had we chosen the other box, so instead of using this box and following it through, we could do the same thing here. So let's do this, but now when we make our Newton's second law equation, we're going to say that the total forces on A is equal to the mass of A times the acceleration of A. And now when we look at the total forces on A, we see that in fact there are three. This one, and this one. So let's put that in. Applied force to the right, take away the friction, take away the force of B on A is equal to mass A times the acceleration of the system. And once again, we substitute in our numbers, 45, take away this. We isolate for FB on A, and we end up with 30 newtons, okay? So in either case, we're getting the same number, and that makes sense because we are calculating the tension or the contact force in between them, and it really should be the same force because each of them are relaying the force to each other. Okay, so I hope that helps to clarify that question. And if you're still concerned about it, then please come and see me and we can chat.